Over COVID break, what I did was make a model kit and research the FW190. First, I used primer on the main parts. Then I assembled the wings and the fuselage. After that, I mask and paint the plane and apply decals. There are still some final tweaks I need to make to fix some issues I had with the plane. Before we can talk about the FW190, we have to talk about its chief designer, Kurt Tank. Kurt was born on February 24th, 1898. Before he worked at Focke-Wulf, he served in the German infantry during World War I. Following the war, he studied electrical engineering at the Technical University of Berlin. After graduation, he began to work in the aviation industry as a test pilot at Albatross until the company went bankrupt and merged with Focke-Wulf. In 1935, the German Ministry of Aviation held a contest to produce a modern fighter. The competitors were the FW190, a low-wing fighter with an open cockpit, armed with either two 7.9mm machine guns or one 20mm cannon mounted in the nose. The Arado AR-80, another low-wing fighter with a Junkers UMO 210 inverted V12 that was able to push it to a top speed of 400 kilometers per hour. This speed was further increased to 452 kilometers an hour with the addition of a constant speed propeller. It had two wing-mounted machine guns and one in the nose. The Messerschmitt Bf-109, featuring two nose-mounted 7.9mm machine guns, boasting a top speed greater than any of its competitors. And finally, the Focke-Wulf FW159, featuring the same Junkers UMO engine as the Arado AR-80. On paper, the FW159 had good specs, but it was hampered by its overwing parasol design that reduced its maneuverability and hurt its pilot's visibility. Before the 109 entered service, the German Ministry of Aviation held another fighter competition in 1937. This time around, Focke-Wulf gave Kurt Tank full authority over the design of their entry in the competition. Kurt said the Messerschmitt 109 and the British Spitfire, the two fastest fighters in the world at the time you began working on the FW190, could both be summed up as a very large engine on the front of the smallest possible airframe. In each case, armament had been added almost as an afterthought. These designs, both of which admittedly proved successful, could be likened to racehorses. Given the right amount of pampering and easy course, they could outrun anything. But the moment the going became tough, they were liable to falter. I had seen the harsh conditions under which military equipment had to work during wartime. I felt sure that quite a different breed of fighter would also have a place in any future conflict. One that could operate from ill-prepared frontline airfields, one that could be flown and maintained by men who had received only short training, and one that could absorb a reasonable amount of battle damage and still get back. Unlike many of its contemporaries, it used a radial engine. Many designers believed that a radial engine would create too much drag on something as small as a fighter, but Kurt was not convinced due to the American Navy's success with its radial engine carrier-based fighters. The 190s used a BMW 801 14-cylinder radial engine. To compensate for the additional drag created by the radial engine, the engine produced nearly double the horsepower the 109's DB601 inverted V12 had. It also featured a NACA engine cowling to reduce the drag created by the massive engine. Initially, the cowling didn't let enough air into the engine bay, causing catastrophic overheating issues. This was solved in the production variants by reworking the cowling shape and installing a fan powered by the engine that spun independently of the propeller at nearly 3 times the speed. In contrast to most fighters at the time, it had wing-mounted retractable landing gear rather than the failure-prone fuselage-mounted landing gear. This is a significant feature since many Bf-109s were lost during takeoff and landing due to their narrow track causing instability issues. On top of that, it was also able to withstand a sink rate of 4.5 meters per second, meaning that anyone behind the controls could land it with a broken engine and half a wing. All 190s featured retractable tail wheels actuated by cable, but the wheel did not fully retract. This was so that in an emergency case, if the main gear failed to deploy, the tail wheel could be used as a skid. The retract mechanism was easily accessible from a triangular hatch in the tail. Nearly all planes at the time used cables and pulleys to actuate the control surfaces. These cables were liable to stretch. This would cause play and slop in the controls, making them feel less crisp and less responsive. Thus, Kurt opted not to use this system. Instead, he chose to use push rods in the ailerons and a bell crank in the rudder. They used the push rods and bearings to minimize the maximum force exerted in the feedback on the ailerons to 3 kilograms, since it was deemed that the average pilot was not able to exert a greater than that. To reduce the pilot's workload while flying, small trim tabs were fitted to the ailerons and rudder, and after initial test flights, only the elevator would need to be trimmed each flight. This was done electronically using a system integrated into the bell crank that consisted of a worm and gear and an electric motor to trim the elevator remotely from the cockpit. Many other systems were operated electronically, such as the landing gear and aircraft. These features were operated through pneumatics, which worked well, but if a Spitfire's pneumatic system failed, the pilot would not be able to fire his guns, deploy his landing gear, or adjust his radiators. I think the amount of electrical systems used in the 190 is due to Kurt's background in electrical engineering.